Hello, and welcome to our Geometry Processing in Matlab with gptoolbox SGP tutorial. This is a tutorial that I'm giving together with Derek and Silvia, who will speak after me. I'll take the first 30 minutes. And the goal of this tutorial is to teach you how to do geometry processing with Matlab using the gptoolbox library, a geometry processing library by Alec Jacobson. We will start by quickly going through how to do very basic math in MATLAB. As far as it comes to basic arithmetic, whatever you write into the interactive MATLAB console, it'll just do it. So 3 plus 5, it does 8. Minus 1 plus 1, it does 0. Multiplications are done with the asterisk, and so on. You get the gist. You can also assign variables in MATLAB. So if I take any sort of letter, assign a number to it, now the letter A is the number 1. We call it like this, and I can also use multiple letters. Here, MATLAB works like a normal programming language. What's special about MATLAB is that it has purpose-built syntax for writing matrices and vectors. For example, here is how you write a matrix in MATLAB. You have this opening square bracket. Then I write the first row where entries are separated by commas. I don't need to separate it by commas here, but I recommend you do it for readability. Then a semicolon gets me to the next row, where I again write entries separated by commas. This is a very easy way to represent any matrix or vector in MATLAB. There is a special syntax for some kinds of vectors. For example, if I do something semicolon something else, for example, 1 semicolon 10, it'll give me numbers between 1 and 10. And if I do 1 semicolon 3 semicolon 10, it'll give me numbers between 1 and 10, but with a step size of 3 in between. And then the last one of these that you might want to remember is a special syntax for the identity matrix, which is simply I. OK, you now know how to create a matrix in MATLAB. What do we do with them once we have created them? So here are 2 matrices in MATLAB. I can add them the same way I could add scalars, the way you might think. I can multiply them. I can multiply matrices, and it does the normal matrix multiplication with the asterisk. I can also do a component-wise multiplication of matrices. So instead of doing a matrix multiplication, we multiply each element of the first matrix with the corresponding element of the second matrix. And in MATLAB, this is done with dot asterisk. The same thing works, for example, if you want to do a component-wise division, which I'm not going to do here. Or if you want to do a component-wise exponential. For example, a squared will multiply the matrix with itself, but a dot squared will do a component-wise squaring of all the elements of A. OK, what is the most important thing we can do with matrices in linear algebra? We can solve linear systems. So here is a vector. We already have a matrix. We can solve the linear system AX equals B using the matrix function inv, which computes the inverse of a matrix. So inv A, the inverse of the matrix A, and inv A times B solves the linear system. This is something you should probably never use. Unless you want to explicitly know the elements of the inverse matrix, there is something much better, which is this backslash operator, a backslash B, which uses the most appropriate linear algebra algorithm to solve your linear system instead of explicitly computing an inverse matrix, which is usually not needed in practice. Here's another neat thing you can do with matrices in MATLAB. We have this dash operator. It means transpose. So this is A transpose, this is A. It just transposed the matrix. The last thing I'm going to show you about how to work with matrices in MATLAB is how to access single elements of the matrix. So let's define a vector. You access elements of this vector with bracket notation. So A bracket 3 gives me the third element in this vector. A bracket 1 will give me the first element of this vector. This also works with matrices, where if you do the single bracket access, you can see it counts in row order. So 3 is the first element, 1 is the second element, and 7 is the third element, and 2 would be the fourth element. If you want to access a specific element of the matrix using both its rows and its columns, it goes like this. So A 1, 2 gives me the element in the first row and the second column. You can, this is more complicated, also select sub matrices using, for example, using vectors as accessors in the brackets. For example, here I want to access the first and the second row and the second column, and it'll give me the appropriate subvector. The last thing I want to show you about MATLAB itself before we move on to specifically geometry processing with gptoolbox is conditionals and loops, which you're going to use a lot when you write scripts in MATLAB. If works the same way it works in most other programming languages. So I can write if true for end, and it'll display 4. If I instead wrote if false, it does not display 4. Loops work similarly with the while end syntax. So I can say while true for end and just print 4s unless I abort it on my Mac. This is Control-C. And there is a special syntax for loops that goes like this: for a variable equals a vector. So instead of 1:5, this could be any vector. And what it will do is it will execute the statement in the for loop for every element in the vector. So in this case, it just printed all the integers from 1 to 5. OK, let's move to the actual geometry processing part of this tutorial. For everything that comes after now, you will need gptoolbox installed. And if you go to the interactive tutorial part that belongs to this presentation, you will find a link to the gptoolbox library together with installation instructions. Install this, and then you will be able to follow along with everything I and after me, Derek and Silvia will be doing. OK, let's start with the most basic structure that we deal with in geometry processing, the triangle mesh. gptoolbox mainly uses one way to store and handle triangle meshes, and it's the vertex list face list structure. It goes that way. We give the vertices as a list where that is a matrix where each row is a different vertex, and each column are the x, y, and z coordinates of the vertices in your mesh. In this case, this is a two-dimensional mesh, so it only has x and y coordinates, and it has 3 vertices: one at 0, 0, one at 1, 0, and one at 0, 1. And then the second list that gets specified along with this is the face list. In this case, our mesh will have one face. It is the triangle with vertices 1. This means the first row of V, 2, the second row of V, and 3, the third row of V. Very important. MATLAB is a language that does not do 0 indexing. It does 1 indexing. So array indices started at 1. Thus, this row here is the first row and not the 0th row. OK, how do we visualize our very simple mesh? This is this tsurf command. It's one of the commands you will probably use most when working with gptoolbox and MATLAB. It visualizes a triangle mesh for you. Here it is. And you can see it visualized the mesh with face F and those 3 vertices. It's a face that goes from vertex 0, 0 to 1, 0 to 0, 1. You might notice that the perspective here is quite skewed. And in fact, when I resize this window, it'll resize the aspect ratio of the plot as well. If you want to avoid this, there is the MATLAB command called axis equal. If you issue this command, then the proportions of your plot will always be the actual physical proportions of your mesh. So no matter how I resize this window now, this triangle has the same proportions. Of course, we can have more interesting triangle meshes than this very simple one with only one triangle. Here is one with 4 vertices and 2 faces. If we plot this one, this is a simple square. You can see it has 2 faces. The face that has vertex indices 1, 2, and 3, and the one with vertex indices 2, 4, and 3. This works exactly the same when you plot meshes in 3D. Here's an example of vertices for a tetrahedron. And here is a face list for a tetrahedron. The only thing that changed here is that my vertice and my matrix with the vertex coordinates now is a 3rd column for the z coordinates. Other than that, it's exactly the same. And here is our tetrahedron in 3D. And in MATLAB, when you have a plot, there are always these widgets on the top right of the plot that you can use to rotate it in 3D. Look around at our little tetrahedron. It's just as easy to read meshes that are provided by other people. You probably won't construct every mesh by hand by specifying the vertices and faces. So if you have something that's given in OBJ format, here I have the Stanford bunny in an OBJ file. I can read it with the read OBJ function. And that's how this looks like. a bunny. And then there's an equivalent command for writing. OK, having created a mesh as a vertex list and a face list, we can now start plotting functions on this mesh. Let's define a function f defined on every vertex of our mesh. You can see the size of the vector f, the same number of rows as the size of the vector b. So for every row in v, for every vertex in our mesh, we have a function value. And the way this is plotted in gptoolbox is we use the c data command in tsurf. So we use tsurf as usual, tsurf fb, and then add c data f. And this is how it looks like. Now, by default, Matlab uses some weird face-based shading, which if you haven't given it face-based data, doesn't correctly represent your vertex-based data you gave it. So in this case, we can issue the command shading interp, and it'll do a linear interpolation and vertex-based shading. If you actually have face-based data here, say, for example, these are the very centers of all of the faces in the triangle mesh. And here is a function defined on these very centers. Then if we issue the command tsurf f, it'll do face-based shading. And this is, in this case, actually what we want. Now, you will notice that the plot we have here is a color plot, which means different color values correspond to different function values. If you ask yourself which color values correspond to which function values, your question is answered with the color bar command. You did this bar on the right that tells you which color value corresponds to which function value. You are not restricted to using MATLAB's classical color map, which is the Parula color map. You can use any kind of color map. For example, I really like Cynthia Brewer's C. Brewer color maps. They are integrated in gptoolbox, and you can get them by issuing the C. Brewer command, where you say which color map you want. And the interactive tutorial that goes along with this presentation has a link to the C. Brewer website that shows you all the color maps that are available. You can apply this to the plot by issuing this color map command. And now our plot is in blue and white instead of in the Parula colors. OK, now we know how to plot functions. Let's talk about a little bit about how to make these plots a little bit nicer. So let's get ourselves a plot back. OK, the first thing we're going to deal with is this grid background. While for some plots, you might want to have a grid with coordinate axes in the background, often this isn't really important and can, in fact, be distracting. We can remove this with the simple MATLAB command axis off. It now looks all uniform and gray, the background, in your MATLAB window. And if you actually save this image as a PNG, it'll just save the background as transparent. The next thing we can add to make our plot more beautiful is a light. At the moment, this is just uniform lighting, where every point of the surface contributes exactly equally to the color that is drawn on screen. We can change this by adding a light. The command camLight adds a light that is at the exact same position as your camera. But you're not restricted to that. You can add lights that come from any kind of position by using the light command. And if you enter help light, it'll tell you exactly how you can modify the parameters of your light to suit your needs. You will see that now we can make out individual triangles. Even though we used the shading interp command before, the only thing that did is it removed the actual triangle edges from being plotted. And it made the function values itself linearly interpolate across faces. It doesn't actually make the shading uniform. In order to do that, we need to explicitly specify that we want garage shading, which in MATLAB is done with the set command. Now, the actual normals are also, that they're used for shading, are also interpolated linearly across the faces. The last thing I'm going to show you on how to make your plots a little bit more beautiful is perspective. You might not have noticed, but this is actually orthogonal perspective. So what you're seeing here is a perfect orthogonal projection of the surface onto the plane of the camera. This is not actually how cameras and eyes work in real life. We use a perspective projection, which you can do in MATLAB by using this camProy perspective command. You can see it changed a bit. The parts that are closer to the camera now appear larger compared to the parts that are farther away from the camera, because this is how your eye actually works. Here's another thing you can do to make your plots a little bit more beautiful, a little bit of a cherry on top. You can add a fake shadow. It won't actually ray trace a shadow for you, but you can add a fake shadow to your plots using the add shadow command. that takes the parameters as a parameter your plot and also the light for which the shadow is to be computed. And this is how that looks like. You can see what it actually does is it projects your mesh onto a ground plane and renders that one in gray. But it looks almost as if your mesh had a little shadow, which makes your plots nicer looking. OK, now that we know how to load a mesh, how to plot a mesh, how to plot functions on a mesh, let us compute some properties of the mesh. And one of the properties of meshes that I use most is the boundary of the mesh. How do we distinguish between the boundary of the mesh and the not boundary of the mesh? Well, we use the following simple gptoolbox command, outline. What outline does is it'll give you a list of all the boundary edges. Let me show you a slice from this outline here. So outline is a matrix with E rows, where E is the number of boundary edges, and 2 columns, where the columns are ordered indices into the vertex list. So that means there is a boundary edge that goes from vertex 7 to vertex 5, and there is a boundary edge that goes from vertex 9 to vertex 7, and so on. And if I only want all the boundary vertices, the way to get this is with MATLAB's unique command, which will just return all the unique indices from a matrix that you input. Now let's look at a bit of the unique of this B vector. It just shows all the boundary vertices now. Let's use this actually to plot a function that will highlight the boundary of our mesh to us. What I did here is I created a vector of zeros with as many zeros as our vertex list has rows. And now I will set all the rows corresponding to indices in B to 1. This is one of those ways in which MATLAB is really magical. You don't need any loop or anything. You just write U of B equals 1. Let's plot this function. Here's how it looks like. Let me remove the grid in the background. The actual surface itself is white, and the boundary is blue. I could have done this with nicer shading. Let me actually repeat the whole thing, a little bit nicer shading. And I've saved in this TFT script all of the shading commands that we just learned, so I don't need to retype them every time. Beautiful. So here we have our surface where all of the interior is shaded in white because I give it the 0 function value, and all the boundaries shaded in blue because I gave it the 1 function value. OK, let's talk about another important property of surfaces, which I use a lot. It is a surface's normal vector. First, let's compute the Perface normal vector of mesh in gptoolbox. This is very easy. This command is just called normals. And ta-da, you get a matrix where each row corresponds to the normal vector of the face that it comes from. So the size of n, size of n is exactly the same as the size of f, because each row of f corresponds to a row of n, and that row of n will be the normal vector for that row in f. However, be careful here. This n are not normalized normal vectors. They are just the raw results of the cross products. And if you actually need unit length normal vectors, then you will need to normalize them. This is done very easily with a gptoolbox like this. What does norm row do? Norm row returns you 1 column vector, where each entry in that column vector is the norm of the respective row in the matrix that you entered into it. And this dot divide is normally a component-wise division, but if the matrix dimensions are just right, the way it is here, it'll smartly figure out that you want to divide every element of the row by the same number that is given by this vector norm row n. So this just normalizes our vector. Now let's plot the Perface vectors that we have just constructed. Here's our surface. The first important command which we need to use here, which we haven't used before, is hold on. In MATLAB, normally when you issue a new plot command, what it does is it clears all the plots that you already have in your figure. If you do hold on, it does not do that. So now we can put another plot on top of this plot, which is the vectors. And we will plot them with QVR, which will do a quiver plot. We first specify the points at which we want to plot our vectors. They are simply the barycenters of our faces. Barycenter is another gptoolbox command. And here are our vectors. You will see we now have tiny little arrows at every point that are the normal vector at each face. Okay, now we know how to create meshes, load meshes, plot meshes, and compute a few basic properties of meshes. However, in order to continue further, for many of the more advanced geometry processing tasks that we will use, we will need sparse matrices. What are sparse matrices? Sparse matrices are matrices that are stored in a more efficient way, since we know that most of their entries will be 0, so we only store the non-zero entries of these sparse matrices. Here is an example of a matrix that is not sparse. It is a dense matrix. And if we issue the MATLAB command is sparse, the answer will be no, this isn't sparse. How do we get a sparse matrix from a dense matrix? Well, let's first start with a dense matrix that actually has a few 0 values. And we can get a sparse matrix by simply issuing the sparse command. You see that AS is sparse, so now MATLAB, when you ask it to show the matrix AS, will only show you the non-zero values. And just to be sure, let's issue is sparse of AS, and yes, it is indeed a sparse matrix. Now, how do we construct sparse matrices? The way we just did is indeed one useful way to construct sparse matrices. If you have a dense matrix and issue the sparse command, it'll automatically convert it into a sparse matrix. However, many matrices that you want to construct are actually so large that you cannot construct the dense matrix from which to construct a sparse matrix from. So there are alternative ways. For example, you can simply construct a matrix entry by entry. This works. However, this is slow if you have to do it for many entries. In general, in MATLAB, issuing commands for each component in a loop or something will be very slow, while issuing vectorized commands for an entire vector at once, that will be fast. So here is the most general way to construct sparse matrices in MATLAB. First, in your mind, you make yourself a mental list of all the non-zero entries of your matrix. Then you construct a vector that contains all of the rows of the matrix in which the non-zero entries will be. Then you construct a vector which will contain all the columns in which your non-zero entries will be. Then you construct a vector which will contain all the values in which your non-zero entries will be. For example, in the 3 vectors that I just defined here, I will have a non-zero entry 1 at row 2, column 2, and I will have a non-zero entry -1 at row 3, column 3. And then we can construct the sparse matrix also with the sparse command, but this time with different arguments. First are 3 vectors, the rows, the columns, the values, and then the dimensions of the matrix. And this gives us our sparse matrix. There is there are a few shorthand commands that'll make it quicker to construct certain kinds of matrices. For example, the SPI command will construct a sparse identity matrix, and there is the spdiags command, which in this particular syntax, when you give it a diagonal and then 0 and then the dimensions of your matrix, will construct the diagonal matrix with the entries of that vector. But this command is actually more powerful. You can also specify off diagonals, and then the second parameter is not 0 anymore. Issue a help spdiags if you want to know the entire syntax. Now let me show you 2 simple examples of sparse matrices in geometry processing. The first one of these is loop subdivision. So here's an example of a very coarse surface. This is a mesh made from triangles, but there's not a lot of triangles. And as a result, the plotted surface looks very coarse, like a blocky model from a very old video game. One way to display a smooth surface, starting with a very coarse triangle mesh, is the classical loop subdivision, which is available in gptoolbox with the loop command. Here, loop vf4, what it does 4 iterations of loop subdivision. And you can see as a result, if we plot the upsampled mesh, it is a nice and fine mesh. And we have this very smooth mug instead of the coarse mug before. What does this have to do with sparse matrices? Well, along every loop subdivision, the vertices move in a linear way, which means that the upsampled vertices VU are actually a linear function of the original vertices V. And you get this linear function back in the form of a sparse matrix S. And we can check that this is really the case by computing the norm of S times V minus VU. And we see that up to floating point shenanigans, this is actually the same matrix. This is very useful. With this sparse matrix, you can take any information that you had on the coarse mesh, for example, a function, and just map it onto your higher resolution mesh. For another application of sparse matrices, this is probably one of the most famous things in geometry processing, certainly the thing that excites me the most about geometry processing, Laplacians. We can compute the usual cotangent Laplacian in gptoolbox using the cot matrix command. You have to do minus cot matrix if you want the positive definite Laplacian, and if not, you get the negative definite Laplacian. We can get the finite element mass matrix by using mass matrix VF. gptoolbox offers a variety of kinds of mass matrices. You can have various kinds of lumped mass matrices. You can have the full mass matrix. To see how to do these commands, do help mass matrix, and it'll explain all the options you have for mass matrices. Yeah, let's try out the Laplacian. We have I have prepared a noisy function that we can look at. This is how that looks like. It is a function, you can sort of see what it's supposed to be, but it's noisy because there's these blips. And now we can smooth it with the Laplacian by solving this linear system, the smoothing factor of 0.01. Now when we plot the smoothed function, all the noise is gone. You have a nice smooth function. Let's do the same thing with an even noisier function. Let's add some noise to this UN to exaggerate this effect. Now let's plot this noisy UN. That's a noisy function. Let's smooth this. We probably need to smooth this a little bit more than just 0.01. Perfect. All of the noise removed. So this is how you compute Laplacians and mass matrices. And this is the perfect high point for my part to end. You can't go much better than Laplacians. And I will now pass my torch on to Derek and Silvia, who will conduct the rest of this gptoolbox and geometry processing in Matlab tutorial. Thank you very much.
Hello everyone, my name is Derek, and welcome to the part 2 of our SGP tutorial on geometry processing with Matlab and gptoolbox. From the previous part presented by Oded, you can already see some advantages of using Matlab to do linear algebra and visualize results on 3D shapes. In this part, I'm going to take a deeper dive and go through 3 different examples to demonstrate why we love to prototype geometry processing using Matlab and gptoolbox. And just a quick preview, really, the main reason that attracts us to use gptoolbox is because many basic utility functions have been implemented. And you already see some of them from Oded's talk, for example, the cot matrix and the mass matrix. And in our first example, we're going to show how handy it is to implement a paper with these utility functions. And our second example focuses on introducing a very, very useful function in gptoolbox called the min quad with fixed. And this stands for minimizing quadratic energy with Dirichlet boundary conditions. And because so many geometry processing algorithms involve minimizing a quadratic program, this function is extremely useful. The last example I'm going to talk about today is another very useful function in Matlab called ICE, which is a function for solving eigenvalue problems and generalized eigenvalue problems for sparse matrices. And again, this is another key subroutine in spectral geometry processing, and we're going to see how handy it is to have this tool. So without further ado, let's start with the first example. So in our first example, we're going to use gptoolbox to implement some geometry processing algorithms. And the paper we're going to focus on today is this paper called the geodesic heat. And this is a method proposed by Crane and Carlos in 2013 for computing geodesic distance. So in other words, given a point at this white spot, this method computes the distance along the surface from this white spot to all the other points on the shape. And this paper basically contains a lot of very interesting discussion and details. But for the purpose of today, we're not going to go through all the details. Instead, we're just going to focus on some essential steps that are required for our implementation. And on the left-hand side, you're seeing my Matlab window. The top block is the script window. Basically, this is a place you type in your script. And the bottom is the command window. And the right-hand side is the workspace that contains the variables. So, and if you want to run your script, you can just click this green button, says run. And alternatively, you can also use the shortcut, which is the option command R in Mac. To begin with, let's start. I usually prefer to start writing my script with these 3 comments. These three commands basically clears all the variables, clears all the commands, and close all the figures, so that whenever you run your script, you always make sure you start with a clean start. So first, before you implement this algorithm, let's just load the mesh for our implementations. We can load this spot model for our implementation. And if we run this algorithm, you can see the face list and the vertex list. Okay, and now let's start implementing this paper. So this paper only contains 3 simple steps to implement. And the first step is to integrate the heat flow for some fixed time t. And the second step is to normalize the gradient of the u you compute from the previous steps to have a unit norm per row. And the third step is to just solve some problem to get the phi. So let's start with the first step. So the first step is to do some time integration. And actually, the implementation depends on which time integration algorithm you choose. In this paper, they're using the backward-Euler integration, which can be reformulated into this single linear system. And in order to implement that, we just need to figure out what are those symbols. So let's first look at the A here. So the A is a B by B matrix, and it's a diagonal matrix containing the vertex areas. And if you remember the tutorial presented by Oded, this A is nothing but the mass matrix functions in gptoolbox. And for the second symbol, the T, and this is a time parameter, you do the time integration. And this is actually very crucial to determine the accuracy of your resulting distance. And this default parameter is written here. It's the T equals to H squared. And the H is the mean spacing between adjacent nodes. So in other words, H is nothing but the average edge length, and the T is just the square of that. So we can just write T as average edge length squared. And this average edge length is also the function implemented in gptoolbox already. So let's look at the third symbol, this LC here. And I believe the LC is written here. LC is another D by B matrix. And this is the cotangent operator. So basically, this we also have seen this function in Oded's talk. It is nothing but a cot matrix function in Matlab. And you can just write down this, and that will give you the LC here. And that's basically everything we need in order to compute the left-hand side. So we can now get a left-hand side equals to A subtract T times LC. That's just exactly write down this formula. So, and for the right-hand side, this is the correct delta function. So basically, this is a function that almost zero everywhere, except you have the 1 at your key source, or your point that you want to compute the geodesic distance from. So in order to get the right-hand side, we can first initialize the 0 vector with size equals to number of vertices by 1. So this is nothing but, if you type in here, this is nothing but a 0 vector with size equals to number of vertices. And let's first randomly initialize a key source. Just say the first vertex will be our key source, and then we can get this delta function by setting the value at this key source we want. And that basically is everything we need to implement this step. So we now can just solve U by using the backslash operator in Matlab. So we have left-hand side backslash our right-hand side delta. And after that, if we run the script, we'll get our U value here. And typically, I prefer to debug this implementation along the way instead of waiting until I write down everything. And a very useful debugging method in Matlab is to just visualize things on the mesh. So if you want to visualize this U, you can just do the T serve FV, and we can do this, define the colored data to be our U. And that will give us on this figure. So in order to see the per vertex value, we can just do this shading inter, and that will give us the vertex value. So starting from this yellow source point, and if we diffuse the heat with a small time step, and this heat will basically flow. And according to this figure, although it is unsure whether the value is correct, but this result makes sense. So I think we are good to go to kind of implement our second step. So our second step is nothing but normalizing the gradient. And to get the gradient U, you can also utilize the gptoolbox function for the grad. This gives us a gradient operator. And if you want to get the gradient of U, it is super easy. The gradient of U can be easily computed by using the G times our U computed from the previous step. And if you run that, that basically is our gradient. And currently, the gradient is a vectorized version. So in other words, originally we have the gradient equals to number of faces by 3, and the 3 is the x, y, z direction. And currently, this is a vectorized version. So if you look at the size of this grad of U, this size equals to number of faces by 3 and by 1, and this is a vectorized version. So just to make it clear, this is a vectorized version of the gradient of U. And in our paper, because we want to normalize the gradient to have unit norm per row, so we have to reshape this vectorized version back to the matrix format. So we can get the matrix format, this gradient, by reshape this vectorized version to have number of faces by 3, and the 3 is the dimension here in our algorithm. And by running that, we're going to get the gradient u as the matrix and equals to number of faces by 3. And in order to normalize the gradient of u version of the gradient of u, we can just do this row-wise division with respect to the norm per row. And basically after this step, the gradient of u normalized will have unit norm per row. And then according to the formula, we want to define our x as the negative of the normalized gradient. So, and the gradient of normalized, and that will give us our x. And for the third step, we solve a Poisson problem. And our left-hand side is nothing but the Laplacian operator, which is nothing but a Codd matrix defined here. So we don't need to do everything to get the left-hand side. And the right-hand side is of the x. So, and then to get the divergence, we can also utilize the function gptoolbox to give us the divergence operator. And in order to get the divergence of x, we just need to do times x we computed from the previous step. But just to make sure this will give us some error because the x currently is a function of the matrix. Oh, I haven't run this script. So this x currently is in the matrix format, but this divergence operator actually assumes that the input is a vectorized version. So what we have to do here is to just vectorize this x. And once we have that, then run the script, and we'll get the divergence of x as a line vector. And in order to get the phi, we can just, again, using the backslash, the left-hand side is our potential matrix, and the right-hand side is our divergence of x, and that will give us our phi solution. And because typically, if you solve this linear system, it's not guaranteed that at the geodesic distance at the source point is exactly 0. So we can ensure that's the case by just doing a constant shift to subtract the phi value at the source location. And once we do that, then we can make sure that we start from 0, which is what we need because the distance from the point itself should be 0. So once we run that, we can get our phi solution. And then, yeah, that's the end of the implementation. So let's take a look at whether the result makes sense. So we can again use t sur f of v, and we get the color data as this phi. And we can also want to look at the vertex function, so we can just do shading curve. So actually, this is the end of this is our phi solution, and also we can also visualize the color bar just to see whether this start from 0. Actually, it is. So at this dark blue location is, I believe this is our heat source, and this start from value 0, and we compute the distance from this point to all the points along the surface. So if you look at the back side of the spot function, you're seeing a yellow color, which is corresponds to high distance value. So yeah, that's the end of the implementation. In our second example, I'm going to introduce a very, very useful function in gptoolbox called the mean quad with fixed. And probably from its name, you can already guess what it does for you. It basically minimizes some quadratic energy in this format and subject to some Dirichlet boundary conditions. So just to be clear, and this function minimizes the quadratic energy in this format with respect to x. And this basically we can read it as like x transpose times a times x plus x transpose times b. And the constraint would be our output x at the location specified by c have value equals to d. And the reason why this is so useful is because a lot of geometry processing algorithms involve minimize some sort of quadratic programs. An example would be the shape deformation, which can be written into this quadratic format. And basically, the problem basically have some user-specified handle indices, and for those handles, user will specify the desired displacement on those handles. And our goal is to solve for the deformation vector b, so that it satisfies these constraints, and at the same time, it minimizes the quadratic energy. And this quadratic energy will be determined by this matrix A. And you can basically craft a lot of different deformation algorithms by using different quadratic energies. But the one we're going to play with here is the Dirichlet energy, where the A is nothing but our favorite potential matrix. So let's see how can we do this shape deformation using equal fixed. So on the left-hand side, I already prepared a toy problem for you. So the first line, just clear all the variables. And the second line is just to reload our mesh. And here is our handle indices, and this is our target handle displacement. So for these 5 lines, I just try to visualize the problem so that you know what we're trying to achieve here. So if I run the script, and this is the figure I will get, basically this is our like example mesh, the spot, and we have some rest spots as those handle indices, and we also have some errors to represent our handle displacement. And the goal is to minimize the quadratic energy I described here so that we can figure out how to deform this free vertices and minimize the derision of energy. Okay, so in order to do that, we just need to obtain all the variables for our min-quad prefix. So our A here will be our potential matrix. So the A is nothing but the cos matrix. And because in min-quad prefix we have this B, but for this deformation energy we have no B at all. So we can actually just initialize with a 0 matrix like that. And because the C and D are just the handles and the D handles, so we can basically solve for that by using the input A and the B and the handles and the D handles. And if we run the script, and that will give us our solution of D here, that will be the displacement vector. And if we want to visualize the deformed vertex, we can just create a figure and do our T-surf FV plus our displacement vector. So it's a deformed mesh, and we can just make the X equals, that it looks better. So if we run that, we can actually get 2 figures. The first figure is our initial settings, and the second figure is our deformed result. And you can see that we drag those handles to our target locations, and we kind of smoothly determine what will be the rest of the vertex positions. And that's basically how we use min-quad prefix. But in addition to that, I also want to share something that is extremely useful. So let's first take a look at this slide again. So in another problem, actually, you have fixed A and fixed C, but you may have different B or different Ds depending on your applications. And for example, in the shape deformation, this means that your handles are the same, but you probably, a user, may drag the handle to different places interactively to see how those dragging operations influence the deformation. Actually, min-quad prefix is supports the prefactorization. And in other words, if we solve this system for the first time, it probably will take a while. But if you have the fixed A and fixed C, and you do prefactorization, and after the first time you solve the system, for the second time, the third time, and all the following times, you're going to spend much less time to get your solution. So let's just take a look at how we incorporate this prefactorization into our code. And actually, this pre-A is, you don't need to do any fancy initialization, you can just initialize it to be empty. But you need to remember to pass this pre-A as the input to the min-quad prefix. And just to make it clear that these 2 things are represented equality constraints, but in the deformation, we don't have equality constraints for now, so you can just ignore these 2 things. And once you pass this empty pre-A here, you also need to pass it as an output so that you can kind of fetch the prefactorization results, so that you can reuse that for your future quadratic programs. So just to make sure you can see everything. Okay, so now this and because the first time we don't have any prefactorization, so let's see how long it takes to solve this. So this tick-tock is the Matlab function to kind of measure the runtime of your algorithm. And if you run this algorithm, you can see that elapsed time is like 0.029. And actually, this is pretty fast because this mesh is kind of low resolution. So in order to see the difference, let's just do the subdivision. Just do a loop subdivision on this model once. So we get a much higher resolution. If I run this algorithm again, okay, and this is the time that is required to solve this linear system. And let's say the user drag the handles in a different location, so we get a new set of deformation vector. For example, I already prepared a new set of deformation vectors like these. And to see what are those deformations look like, so we can also visualize that deformation vector. Let me just comment out the previous drawing plotting functions, and these are we plot a new problem we try to solve here. So we can run that, and this is the new problem we try to solve. So you can see that we still have the same set of handle indices, but we kind of drag the handles to different places. And if we want to solve for the deformation again, we can actually just do this. But this time, because we already have the pre-A computed from the previous step, so we can actually reutilize the pre-A. And just to be more precise, if you type pre-A, you'll see like a specific structure that contains the pre-computation information. You don't need to worry about like what are those fields means, but basically just means that the pre-A is no longer an empty vector or empty thing. It actually contains the useful information for you to speed up your computation. And for the next iteration, if we want to solve the new deformed vertices for our new handle displacement, you can actually just do that. And then if we run this algorithm, the first tick-tock represent like the first time we solve the system. It takes like about 0.15 seconds. And if you want to solve it the second time with the same A and C, but with a new like handle displacement, you can actually we just need like 0.01 second, which is like 15 times faster in this example. And again, like just to make sure we solve the system correct, we can actually also plot the result, which can solve a new displacement. And you can see that this is our new problem, and this is our new results. And the high-level story is that you can simply just put in this pre-A in both input and output, and you're going to be able to accelerate your algorithm much faster when you want to solve the similar quadratic programs for the next time. So in the next example, we're going to introduce another very useful function called Eigs in Matlab. And this is a function for computing eigendecomposition of some matrices. And again, this is a very, very important subroutine in many geometry processing algorithms, especially spectral methods. And today we're going to just look at an example called the spectral conformal parameterization. And this is a beautiful paper actually proposed at SGP in 2008. And the problem they try to focus on here is that give a 3D mesh as an input with some boundaries highlighted in red. And the goal of this method is to compute a 2D parameterization like the one shown on the bottom right here of this 3D mesh. And this has many applications such as like texture mapping. And again, this paper contains a lot of very important and interesting details, but because we don't have a lot of time, so we're just going to skip through them and just look at the equation that is most relevant to our implementation. So in order to implement that paper, actually it boils down to solving a single generalized eigenvalue problem, showing equation 5. And again, like this paper, this is just a simplified version of the solver. Actually, this paper recommends to use the method proposed in section 3.4 for the implementation. This is like faster and more robust, but for the purpose of introducing Eigs, we're going to implement a simplified version, which is nothing but this like equation 5. So first, let's look at what's U here. So the U is the like variable we want to solve, and this actually is the vectorized version of the UV coordinates. So UV coordinates is nothing but like the x, like a 2D plane with x coordinates and y coordinates. And this U vector, basically you can think of the upper half of this U to be the x coordinates, and the bottom half of this U will be the y coordinates. So because of this reason, the U actually has a size equals to 2 times the number of vertices. So all the matrices like LC and a B here in this paper, they are all 2D by 2D matrices. So in order to implement that, let's first start by loading a geometry. And in this case, because we need a mesh that has boundary, so we're going to load this ogre model instead. And to let you take a look at this model, we can also plot that. So I run it, and that will give us the ogre model, which is the example mesh that we're going to use today. Okay, and to implement that, let's first take a look at what is this LC here. So the LC is actually described above here. The LC is a matrix that equals to LB minus A. But what is LB? Then the LB is a 2V by 2V matrix containing the cotangent coefficients. So basically just a block diagonal version of the Cot matrix. So in order to build LB, we can first build our favorite Cot matrix as usual, and this will be like a V by V matrix. V by V matrix. And in order to get an LB, we can use the repdiag function in Matlab. And this function basically replicates the input matrix along the diagonal by the number of times you want it to replicate. And in our case, we'll want to replicate this top matrix L by 2 times along the diagonal. And this will give us a 2V by 2V matrix. So that's our LB. And what is the A here? what is A here? And the definition of A is actually written here. And this in gptoolbox, this is corresponds to a function called a vector area matrix, which takes the base indices as an input. But there's a small tiny detail here. Because of the implementation, actually it differs from the definition of this vector area matrix by 2. So we have to apply 2 times this matrix in order to make sure the scale is correct. So that is our A. And basically that's all we need in order to build our LC here. So we can build LC as LD minus A. So yeah, that's this left-hand side. So we can go back to this eigenvalue problem here. Okay, that's our left-hand side LC, but what is the B here? So the B is another 2D by 2D matrix, and it's a diagonal matrix with 1 at each diagonal element corresponds with boundary vertices and 0 elsewhere. So basically, it's a diagonal matrix, and it will be 0 almost everywhere except 1 for the boundary vertices. And to get that, let's first extract the boundary vertices. And to do that, it's also very simple in gptoolbox because we have a function called outline f in gptoolbox, and that gives us the boundary edges. So if we get the boundary edges, we can do this outline of f. And if you look at this B edges, this is like a list of edges that lies on the boundary, but we don't want the boundary edges. We want the boundary vertices. So we can actually extract the boundary vertices by using the unique function in Matlab, which basically takes a vector or a matrix as an input and outputs a set of unique indices. And in this case, once we take the unique indices of the boundary edges, we're going to get a unique vertex indices. So we can try that. And this B index will be our unique boundary vertex indices. And if you want to get a diagonal matrix with 1 correspond to boundary vertices, in other words, basically the rows and the column indices of those ones will be our boundary indices. And in order to build that B, let's just build it like block by block. We'll first build the top left B by B block of the B, and we can replicate that along the diagonal, similar to what we did for the LD here. So to build the top left block, we can actually assign the row indices as the boundary indices, and the column indices also be the boundary indices, and the values as we will have a list of 1s equals the length of boundary indices, and we can use the method to build the sparse matrices presented by Oded to build the sparse matrix B, and we just build like a top left block of that. So we can do that sparse, and we take the row indices, we take the column indices, we take the values, and we also need to specify the size of the matrix. So the size will be V by V, and that will be the first upper left block of that B matrix, and you can see that B. And in order to get the actual B with size 2V by 2V, we can just do the rep DAG with this block with 2 times. So that will give us our B matrix with size equals to 2V by 2V. And yeah, and that's everything we need. And the last step is just to solve the eigenvalue problem with eigens. And so we can get the eigenvector and eigenvalue using this eigens function. And the input will be our LC, which is our left-hand side, and the B's is like our mass matrix here. And we also need to specify the number of eigenvectors we want to solve here. So for example, we can specify to be 5, and then we will sort the eigenvalues starting from the smallest one. So right now we can run the algorithm to solve this eigenvalue decomposition. And after we wait for a few seconds, here's the eigenvalues and eigenvectors. And because we are using like a 2V by 2V cotangent matrix, so there's small detail is that like actually the first eigenvectors of the solution will be a constant, which is like somehow useless. And the second one is also be the constant, another useless eigenvector. And what we want to use for the final parameterization is actually something called a figure vector. And in this case, it will correspond to the third eigenvector. So if we take the third eigenvector as U, this U will be our vectorized version of the UV coordinate. So in order to get the final UV coordinate, we can just do another reshape of this U to have size equals number V by 2. And that's the end of the method. Actually, once we solve this step, then we have the final parameterization we want. So now we can visualize that. We can first visualize the mesh, the serve and we can make the axis equal. And we can also plot another matrix, which is the UV coordinates. And we can run this algorithm and wait for a few seconds. And then this is our input mesh, the ogre model, and this will be our UV parameterization of that ogre model. And yeah, then that's it. That's basically how to implement a simplified version of the spectral conformal parameterization. And you can see that the size is pretty fast and then robust and super easy to use. Hope from these examples, you can immediately see the benefits of using gptoolbox to prototype or to kind of implement some geometry processing algorithms. But what I have covered so far is just a small part of gptoolbox. So I strongly encourage you guys to kind of explore this gptoolbox or to explore other functions in Matlab afterwards to see whether those functions could be beneficial to your research. And personally, I really think that like prototyping things in Matlab is super convenient because you don't need to spend too much time compiling your code or to debug your code. And once you have a Matlab version, converting to C++ is also not so difficult. And that's the end of my part. Hope you all enjoy it.
Hi everyone. If you've made it this far in the tutorial, you've seen Oded show you many of the basics of using Matlab and using gptoolbox, and then Derek showcased just how useful and easy to use they can be by implementing some very well-known existing geometry processing papers. Now, in what's left of this course, I want to focus on the power of Matlab and gptoolbox for prototyping your own research specifically, and I'll use this as an excuse to go deeper into some key functionality that we haven't covered yet. Now, most of us, when we start playing around with an idea in our head and we want to see how it works in code, we don't go straight to trying it out on those relatively complicated 3D meshes that you've seen in this course so far, right? Usually, we start with very simple toy problems in 2D. Fortunately, gptoolbox is really useful for quick 2D prototyping. Now, I don't know about you, but in all my research projects so far, there's been a moment when me and my co-authors are staring at a whiteboard together, and someone draws a 2D shapes and they say, oh, I bet this would be the shape that would break the algorithm that you're suggesting, or I wonder what our code would do if we give it this shape. Well, inspired by these conversations exactly, there's a gptoolbox function I want to tell you about, which is called getPencilCurve. We call it like this, without any arguments, just one output argument v. And what it'll do is it'll open a figure window, and on it we can draw whichever shape we want. For example, in one of my latest projects, we thought that maybe a C-style shape would break the algorithm. So we can just draw it like that by dragging our mouse, and then just lift it to finish the shape. Now, once we've done that, we'll store this shape as a list of points in this matrix V. Just like we saw, we stored vertices for a mesh before, but now in 2D. And if we want to plot it, we can just use MATLAB's native plot command. There you go. Okay, but if what I want to do is solid geometry processing, I don't just want a polyline like this one. I would want a triangle mesh of the inside of this 2D shape, right? There are many very cool third-party libraries for 2D triangulations. Specifically, there's one called Triangle that's very useful and includes a lot of functionality. And if we wanted to use Triangle, which comes mostly as a command line interface tool, with this shape, we would need to probably export it from Matlab into some format that Triangle knows how to read, and then install Triangle and use Triangle on the command line, and then maybe export an OBJ or PLY file for the triangulation, and then import that file back into Matlab. One of the many cool things that gptoolbox has is it includes wrappers for many third-party software like Triangle. So for example, if I want to create a triangulation of this set of vertices, I can just do a call to triangle like this. I give it v, the set of vertices, and I can then plot this surface. Now, as you can see, the triangulation that I got isn't actually triangulating the C shape that I wanted. It's triangulating its convex hull. Now that makes sense because we haven't given Triangle any more information about the connectivity of the point. So it doesn't actually know that we're triangulating a closed polyline, we've just given it a set of vertices. Now that's fine. All we need to do is we need to specify the edges, so the connectivity of the vertices. In this case, since we're ordered, all we're going to do is say each vertex is connected to the next, and then the last vertex is connected to the first one. So we specify that it's closed, and we'll do this as an index matrix, the same way we define the phase matrix for a triangle mesh. Then this will be an index matrix that connects each. So the 42nd vertex is connected to the 43rd vertex, and so on, and then the 60th vertex, which is the last one, is connected to the first one. Now we can pass this as a second argument to triangle to specify, I want you to triangulate only inside this closed curve. So same call as before. I'm going to add an empty argument that I'm not going to talk about now. And then we get a triangulation of the right thing. Or rather, a triangulation of the right thing, but not a good triangulation, right? Because many of the triangles have very small angles, and it would probably give very low quality results if I were to use this to solve a PDE, for example. Okay, so to get the correct triangulation triangle, the third-party software includes many command line switches. For example, we can specify the maximum area. We were using it in the command line. We could specify the quality of the mesh in terms of the maximum angle, minimum angle. In gptoolbox, we can use those flags the same way. So in our call to triangle, we simply add an extra argument called flags, and use the flags the same way they show up in the triangle documentation. So let's say we want a 20 minimum angle, and then a fairly small triangle size so that we get enough triangles. And that's it. Once we do that call, we can again plot the shape. I'm going to add the axis equal already. And we'll get a decent triangulation of what we wanted, right? This would have been a process that would have taken me maybe drawing this 2D shape on some 2D illustration software like Photoshop or Illustrator or Microsoft Paint, then export that somehow into a Matlab readable format, then export that to triangle, use the triangle command line interface to get a triangle mesh, and then import that triangle mesh back into Matlab. But with gptoolbox, we've done it in just 2 lines of code. One get pencil curve, and then one call to triangle. So that's one of the very powerful things of gptoolbox for prototyping. I'm talking with my co-authors, I come up with a 2D shape, and it takes 10 seconds to run your code in that 2D shape. So let's pretend the code I'm researching is solving a Poisson equation in this shape, just so that we have something to try on. The way we do this in 2D is by using the same commands that Derek showed you in 3D, right? So for example, we have our cotangent matrix. We just give it the same arguments. It'll notice that it's in 2D and do the right things in 2D instead of 3D. The mass matrix, same thing. Then to get the boundary, to impose boundary conditions, again, we just need to do the outline and take the unique elements. And the values that we're going to impose on the boundary are going to be 0. So we just need a vector of zeros that's the same size of BC. So I'm just going to do 0 times BC. This is a specifically MATLAB trick because there's no difference between integers and floating point numbers. So we can do just that. And then we'll just call min-quad with fix, as Derek showed you, with the cotangent matrix. The mass matrix, I'm going to multiply it by a vector of all 1 so that we're solving a Poisson equation, and then impose the boundary condition. Okay, so let's take a look at that solution. I'm going to plot it as colors. Like I think Oded showed you this. It looks something like this. That seems like an all right Poisson equation solve, right? Now, if we want to make an even nicer representation, sometimes colors are fairly hard to see. We could even add it as a height parameter and add all of those gptoolbox functionality that Oded already showed you for nice 3D plotting. We'll get something like this. Let's remove the grid and the axis. Maybe add some lighting. And we get a 3D shape that, if we were writing a paper and solving Poisson equations, this could already be a didactic paper figure. Now that was a very simple example, right? I just drew a curve in 2D and I ran our supposed research algorithm on. But sometimes we want to try on more complicated 2D shapes before jumping straight to 3D, right? So we don't want to do it on those complicated 3D meshes yet. We want to robustly test our 2D algorithm before jumping 1 dimension. Fortunately, gptoolbox has one key function that makes this very easy and sometimes even a lot of fun. So for example, I went on Google Images and I found this image of the Toronto skyline. I promise this is the file I downloaded from Google Images. You can probably look up Toronto skyline PNG and find it yourself. And I have this on my downloads folder. So just like that, I can call one key gptoolbox function called Png2 Poly, which, as you can guess, all it does is it takes the silhouette of a PNG file and it converts it into a polyline in Matlab. So something like this. And then I'll add 2 more arguments that I won't tell you about just yet. And we get a list of vertices, just like we had before, and a list of edges, just like we constructed before. And we can plot them with the function plot edges to see that we have, in fact, imported the right thing into Matlab. It might take a little bit because it's a lot of edges. Now you can see that there are some rasterization artifacts in the polyline that we output, and if our algorithm has some like local properties, that might mess up our the functionality of our algorithm. So fortunately, Png2 Poly includes a smoothing that it can do on the silhouette right after it imports it. So and that's what this second argument is for. So for example, we can tell it to do 10 smoothing iterations, and that might take a while, but you'll see the figure update, and we'll see that now we have a smoothed out version of the Toronto skyline. Okay, great. Now the same way we did it before, we could call triangle, and with the same arguments, I'm going to make the minimum area a little bit larger because we're working at a different scale. And with the same call to triangle, we can obtain a triangle mesh of the Toronto skyline. Now with this triangle mesh, we can again use the same commands that we had before to try out our algorithm, which in this case solves a Poisson equation, and just plot it like we did before. That's it. That's the solution to the Poisson equation. And similarly, we could, like we did before, add it as an extra dimension and have something already very similar to a paper figure that we can have in the 2D section of our paper. If the edges are annoying, we can always call the plot function with f alpha, which decides the alpha value for the transparency value for the edges and the faces. And then we would completely remove the edges and get something that looks a lot like a paper figure already. So at this point in prototyping, we seem to be happy with how our algorithm works in 2D. And we now want to move on to trying it in 3D. But it might be too large of a leap to jump straight to trying it on the common 3D meshes like the bunny or the armadillo or the other meshes that we saw in this course. Sometimes when we go from 2D to 3D, we want to start with simple meshes that we can generate procedurally with different edge sizes and different discretizations, so we can get a better understanding of how our algorithm is working in 3D. Fortunately, gptoolbox includes many ways of generating 3D geometry procedurally. For example, we can start by generating a sphere by calling subdivided sphere, which will generate a sphere by subdividing an icosahedron. This number that we give as an argument, I chose 5, but we could choose any number of subdivisions to pick the level of coarse or fine discretization that we want for this sphere. Now, similarly, we can generate a cube by using the cube function in gptoolbox, and the cube can be generated with an anisotropic discretization, so we can choose it to be more discretized in the x direction and less discrete in the y direction. But in this case, we're going to choose the same just to make it easier, and see how we've generated a cube procedurally. We could have chosen any number of samples on each edge, and we would have gotten a different cube. So this is a nice way of generating shapes with different discretization values so that we can test just the limits of our algorithm before we jump to more complicated shapes where we may not be aware of what's happening all the time. Another shape that we can use is a cylinder, using the function cylinder mesh from gptoolbox. I'll give it the inner radius and the number of samples, 50. Now, if any of these functions you forget exactly what the arguments need to be, you can always use help. And every gptoolbox function has a very clear list of their required inputs, their optional inputs, and what the format of the output. So if anything, if you forget the order of these arguments or anything like that, you can always call the help. And with this, we generate a cylinder. Now, this cylinder is obviously too coarse to run our Poisson solver, but we can subdivide it by using another gptoolbox function called upsample, which simply adds a vertex and turns every triangle into 3. It's not doing nothing too complicated here. We choose the number of iterations that we want to sample. Let's say 3. And we get something that's already looking somewhat decent. Maybe not a great mesh, but at least it has enough vertices that we can see a solution if we plotted it. So now that we have this mesh, we can call our Poisson solver to doing the same commands that we did before, because gptoolbox functionality works just as well if we give it a 2D triangle mesh or a 3D triangle mesh. So we can usually lift our algorithm from 2D to 3D fairly easily. Build a cotangent matrix, a mass matrix, pick the boundary values, and call main-quad with fix to get the solution, and then plot the solution with the color of U. Now that's a bit confusing because of the edges, so I'm going to delete the edges, and also use the phase interpolation color to make it clear. And look at that. That looks a lot like a Poisson equation solution on this 2D surface of a cylinder. Now, you may be thinking that this is still kind of a 2D example, right? Because even though our vertex matrix has 3 dimensions in this case, we're still doing a triangle mesh in a 2D surface, even if that surface is now embedded in 3D, because it's the surface of this cylinder. If we really wanted to do solid geometry processing in 3D, we would need to build a tetrahedral mesh. To get a tetrahedral mesh, the first thing we need is a closed triangle mesh. So for example, let me choose a sphere with the same command I used earlier. There's a sphere, right? Now for tetrahedralizing this closed surface, there are many third-party software that are really, really good and incorporate many state-of-the-art techniques for tetrahedralization. So with gptoolbox, we don't need to write our own complicated tetrahedralization code. Instead, we can use one of those wrappers, again, like Triangle, but in this case, to Tetgen, another piece of third-party software. We call it, just like any Matlab function, we pass it 3 output arguments, which are going to be our vertex list, our tetrahedra indexes, on our boundary faces indexes. And we call Tetgen, just like that, and give it as inputs the surface that we want to tetrahedralize the inside of. That's it. Now in V, T, and F, we're going to have a tetrahedral mesh. V is going to be the set of vertices, just like for a triangle mesh. T is going to be the indices to each individual tetrahedron, like we did for a triangle mesh, only this time there are 4 columns instead of 3. And F is going to be the set of boundary faces of the tetrahedral mesh. F is very useful because if we want to plot the tetrahedral mesh, we usually don't plot every tetrahedron, we just plot the ones on the boundary. So we can always do this. And of course, we're going to see the same thing because we started from these triangles. Now, solving a Poisson equation on this tetrahedral mesh is fairly straightforward using gptoolbox. Again, we can use the same functions that we use for a triangle mesh, which also have tetrahedral mesh functionality. So for example, we can build the cotangent matrix by passing V and T this time. Similarly, the mass matrix. Now, of course, the boundary, we already have it. It's the faces in the matrix F, right? So to get the boundary vertices, all we need to do is find the unique elements in the matrix F. And again, to set the values, I'm going to do make it be 0 in the boundary. So I can do that only in Matlab trick to set the boundary condition. Now we just need to call main-quad with fix as we did before. And we have a solution in U. Now, this solution is hard to visualize because if I just plotted the tetrahedral mesh with the color according to this solution, you would only see one color because the boundary, which is the only thing you see, is exactly where I'm positioning my boundary condition, which is 0. So it's usually very hard to visualize a scalar information on a tetrahedral mesh. Fortunately, gptoolbox comes with a function called sliceTets, which, as the name suggests, basically slices a tetrahedral mesh so that you can look inside. Now, this function might be a little scary because if we look at the help, we need to give it a plane that we need to define in a specific way, and we would need to maybe look at which planes to define and maybe do a loop or something like that over different planes. We could perfectly do that, but one really cool thing about gptoolbox is that usually you can find simple examples of how to use each function in the help. So for example, here it seems like we have an example of visualizing some function, specifically a Poisson equation, on a tetrahedral mesh. And we see that the scalar field that they're visualizing is called h. So something that usually works with gptoolbox is you can just call our solution h, and then just copy and paste all of this. And most of the times it just magically works, and you can visualize whatever it is you wanted to visualize. So in this case, we can see that even though in the boundary it's always red, it's always 0, our solution has some interesting values in the inside. And this would be really useful for debugging. So we seem happy with how our algorithm worked on that tetrahedralized sphere, but that was still a very simple 3D case, maybe the simplest 3D case we could think of. Sometimes we want some intermediate 3D shape on which to test our algorithm before we jump to existing complicated triangle meshes that have much more high frequency detail, and we may not be as sure of what's going on at every moment. One way of generating this set of intermediate shapes is with a method called constructive solid geometry, which just means we do booleans of primitive shapes to obtain more complicated geometry. So I'm going to show you an example of that we're going to do entirely with gptoolbox's functionality. Let's start with the sphere. I'm going to use the same sphere we had before. There you go. And I'm going to do the intersection of this sphere with a cube. To do that, I'm just going to generate a cube mesh with the same commands that we saw before. I'm going to rescale it because this cube, as you can see, if I plotted it right now, the cube shows up on one of the corners of the sphere instead of being centered at the same center of the sphere. So I'm going to just rescale it by first moving its center to the origin, and then rescaling it. And now if I plotted both, let me clear the figure. If I plotted both of these shapes, you can see that they have a non-trivial intersection that might be interesting. Now to compute the intersection of two shapes, we just need to call a gptoolbox function called mesh boolean, and we give it the first mesh. In this case, since it's an intersection, the order doesn't matter, but if we were doing a subtraction, we would need to be careful with which one comes first. Let's give it the sphere mesh, and then the cube mesh. And then we tell it which Boolean operation we want to do. So in this case, intersection. And if we plot this, let's clear the figure first. If we plotted this, we can see that we get exactly the intersection between these two shapes. Now this is a pretty awful mesh, but that's fine. All we wanted is the exact intersection, right? And that's what we got by calling mesh boolean. This is already a fairly complicated mesh, and we could perfectly tetrahedralize it and run our Poisson solver on this shape and see what the solution looks like using the visualization we just saw. However, I want to make things a little bit more complicated. Maybe I have an inkling that if I try my algorithm on a non-zero genus shape, it'll look different, or maybe it'll break the algorithm. I want to make sure it works. So before we run our Poisson solvers, let's add some holes to this shape. I'm going to add cylindrical holes on each of the dimensions. So let's start by constructing the mesh of a cylinder. Again, we just need to call a gptoolbox function, and in this case, we're going to use the caps true argument so that it knows to give me a closed mesh with the top and bottom of the cylinder filled out, so that we have an equivocal concept of inside and outside, so that the concept of mesh boolean makes sense. Okay, so now if I plot this cylinder, you see that it comes out on the top, so it will create a hole there if we did the mesh boolean, but it doesn't come out in the bottom. And I want it to be a hole that goes all the way across. So to do that, I'm going to rescale the cylinder, and I'm going to displace it to the bottom a little bit. And now if I plotted it, you can see that the cylinder comes out on both ends, which is what I wanted. Now I want to create two more cylinders, one on each dimension, and to do that, I'm just going to multiply the set of vertices for this cylinder by a rotation matrix, copy the same triangle set, and create two more cylinders. So this is what we want, right? Now we can do the union of all these cylinders. Let's do it in a new mesh that I'm going to call V cylinders and F cylinders. Use the same mesh booleans function and give it the set of all the meshes. With this API, we can give to mesh Boolean any number of meshes, and it'll just do the union of all of them. It doesn't need to be 2. Union. And now I'm going to clear the figure, and you can see that this creates the union of all the cylinders that we want. Now we can deduct this from our original mesh. Remember, this is what it looked like. And let's deduct our new cylinders from it by, again, calling mesh Boolean. First, the shape we are subtracting from, which is WH, and then the shape that we are subtracting, which is our V cylinders and F cylinders. And the name of the Boolean operation, strictly speaking, is a subtraction, but the mesh Boolean argument is minus. And now if we plot this, you can see that it does exactly what we wanted. It creates this mesh with 6 holes that has non-zero genus, but still we've generated procedurally, so we could change a lot of the parameters and get similar shapes. Now, of course, we could tetrahedralize it by calling tetgen, and with that tetrahedralization, define the same differential operators to solve a Poisson equation, and again, visualizing using slice stats. And now we can see the solution on this procedurally generated shape of our Poisson solver. This can be useful because we can make these holes arbitrarily large, arbitrarily small. We can add more of them. We can make the shape more complicated. We can increase the resolution of any of the shapes that we added. So this is a good intermediate step when we're trying an algorithm before we run it on some complicated mesh we find on the internet. You may be wondering, how is this mesh Boolean algorithm implemented in Matlab? Naively, if we want to intersect 2 meshes, we would need to consider every pair of triangles, one taken from one mesh and the other taken from the other mesh, and see if they intersect, and if they intersect, find out how, do some math to figure out how they intersect, and then maybe stitch the meshes together. That would be a number of calculations given by the number of triangles in one shape times the number of triangles in another shape, which would scale catastrophically if we're doing this for meshes with hundreds of thousands or millions of vertices. Now, as you may already know, the way to avoid this in the literature is to use a more complicated data structure than this list of vertices and faces that we're using, called a bounding volume hierarchy. This is slightly more complicated, and it's very hard, if not impossible, to implement in Matlab. But if we use gptoolbox, this is still not a deal breaker, because Matlab includes a framework called MEX that we can use to call C++ code from Matlab effortlessly. So if I wanted to look at my mesh Boolean function, I see that all there is in this function is a health file. In fact, the functionality of the mesh Booleans is in a C++ file that I'm calling from Matlab without any issue because I've compiled these MEX files. In other words, Matlab is very useful for prototyping and for everything that you can't do on Matlab. If you really need the C++ performance or some C++ functionality, there are still ways that you can import that into Matlab. And once you've done that work, then calling those functions can be done with the same API as with you call a Matlab function. I bet you hadn't realized that mesh Boolean was this complicated C++ thing when I just typed mesh Boolean before. Now, in the GitHub repo associated with this tutorial, there's a whole item dedicated to MEX functions, where not only I give you detailed compilation instructions for the ones in gptoolbox, and I go deeper into some of the examples, but I also teach you how to make your own MEX function by showing you the different C++ functions that you need to make. And if you don't know C++, then you shouldn't be scared, because I've given you these template files that you can use with specific instructions of where to add your functionality. That should work if you're not very confident with C++, but you just need to use this very, very specific data structure or call this very specific C++ function just once and then import that into Matlab and then call it from Matlab without any problem. Okay, so now we're happy with our algorithm. It seems to work on our simple 2D shapes, on more complicated 2D shapes. We've done the very simple 3D Tet meshes. We did even a slightly more complicated 3D Tet mesh. It is usually at this point of prototyping where we try it on a more complicated mesh. So for example, I have my bunny shape saved somewhere. There you go. I'm going to tetrahedralize this bunny. Use the same differential geometry operators we had before. And let's visualize what the Poisson solver does for this shape. Now, I'm sure this is going to work because I prototyped robustly on many different shapes. And there you go. Poisson solution on the bunny. Thank you very much for watching, and thank you very much for following this whole tutorial. I hope to see you around.